Okay, so welcome back to another video. So here we want to evaluate this following limit, but before we get to that, we have that if a is a positive number, so a strictly greater than 0, then let the function j of a equals the improper integral over the positive reals of 1 divided by a plus x multiplied by 1 plus a squared x squared dx, and then another function k of a is equal to the same bounds, but 1 divided by 1 plus ax times a squared plus x squared dx. So we want to evaluate the limit L as the limit as a approaches 1 of k of a divided by j of a to the power 1 divided by a minus 1. So that kind of seems a lot to deal with, and you're probably thinking that we'll probably have to single-handedly calculate these two integrals on its own separately, but there's a trick to actually do this, and we're actually going to call a generalized integral. So there's actually going to be another variable involved in this integral that we're calling. So two variables in this sense. So we want to find its general closed form and then plug in whatever the limits that we need for that in order to associate to help us get to achieve the limit where we're going through. So there's actually really a lot of calculus involved, so you can guess more integrals, but also there's going to be some limits and a special rule involving that limits that actually helps us evaluate our given limit that we want to calculate. And there's actually, I'm not going to get too much of the nitty gritty because there's some parts of the procedure that that actually allows you a lot of time that you need to put in the tedious work into it. So I will actually just let you know when I'll leave that exercise separate for you guys to verify. There's actually a couple of them that actually takes a long time to deal with, but I'll let you know when that actually happens. But with that, why don't we actually just jump right in. So let's actually call the function u of a b, and it's also work only. We're going to let b be a positive number, so I'll actually put that condition in a second. So we have the integral from 0 to infinity of, so let's see, I'm going to write the denominator first. So a plus bx, and then multiply by b squared plus a squared x squared. And then, of course, I'll just write the dx on the top. So that means we're going to let that b be greater than 0, a positive number. So it's worth noting that you can tell that j of a, if you plug in the correct numbers, this is the same thing as u of a comma 1, and then k of a is going to be equal to u of 1 comma a. So it's just worth noting to put this here. So now, with this being the case, let's actually use our generalized integral. So the integrand specifically, let's actually kind of break that up a bit to make things a little bit easier for us. Our integrand that we're dealing with. So in order to actually break this up, we're gonna have to apply partial fraction decomposition. And this is where I mentioned that, again, this actually takes a lot of work to actually break this down. So I'm gonna leave this as an exercise for you guys to verify. A homework exercise, we'll actually put it like that. So have fun with that. I actually went through it. It's a lot. So if you actually use the partial fraction decomposition to this integrand of our rational function over here, we're going to get the following. So our denominator, we're going to get bx plus a, and then multiply by a to the power 4 plus b to the power 4. Our numerator is going to be b squared, and then simply add this with, so again, our denominator, so that's going to be a to the power 4 plus b to the power 4 multiplied by a squared x squared, and then plus b squared. Our numerator is going to be a minus bx in parentheses multiplied by a square. Okay, so with this being the case, then now let's actually go back to where our generalized integral we want to substitute so that we can actually substitute this back into over here. So therefore, that would means u of ab is then equal to, so of course we have a to the power 4 plus b to the power 4. That is not dependent on our variable x, so I can actually factor that outside of our integrand or integral. So 1 divided by a to the power 4 plus b to the power 4. What I'm going to do here is that because this is an improper integral from infinity, I'm going to take that into a form of a limit. So I'm actually going to let this, we'll call this capital N, approach infinity. Then we have our three integrals that we need to calculate. So actually to split this up because we have three terms, 1, 2, 3 in the inside after distributing the a squared into it. So then now we're going to have the integral 0 to capital N of b squared divided by bx plus a, then dx. Add this with the integral from 0 to capital N of a cubed, then divided by a squared times x squared plus b squared dx, and then subtract the integral 0 to capital N of a squared bx, then divided by a squared x squared plus b squared, and then dx. Then we close that off. Then basically everything over here, it's actually pretty simple to calculate for finding its the definite integral for these three. So why don't we actually get to that. So then to reevaluate u of a comma b so far, then that's going to lead us with just, so let's see, we still have our constant 1 divided by a4 plus b4. Then of course we haven't taken the limit yet, so n as approaches infinity. So in here, so our first integral over here, if you calculate its definite integral, we're going to get just b ln of bx plus a. And I'll leave space in the end to actually write our bounds to calculate from 0 to n in just a sec. I just want to put everything out together since because all three of the integrals we're actually evaluating at that same bounds as well. So I'll put it together as one. So our second integral is going to be a squared, then divided by b, and then arctan of a times x divided by b. Then the last integral is going to be b divided by 2 times ln of a squared x squared plus b squared. All right, and then we're going to evaluate this from, of course, 0 to capital N. And then to simplify things further, so actually before we get to the step of calculating our bounds, we have two natural log functions. So let's simplify things further by actually using its natural log properties. So that means it's a minus, so that means we have a division. We actually have a rational function inside of our natural log. So then the limit as n approaches infinity, so that means I have b times the natural log of bx plus a, and then divided by the square root of a squared x squared plus b squared, and then we can just close that off, and then we just still have this function over here, the arctangent. So plus a squared divided by b, and then arctan of a times x divided by b, and then evaluate this from 0 to capital N. And then continuing forward, just plug in n and 0 into the entire thing. So we have 1 divided by a to the power 4 plus b to the power 4. Still have not taken the limit yet, so we still have to write that down. So if I plug in n and 0 for everything and then take the subtraction, we're going to have b times the natural log of b to the capital N plus a, and then divided by the square root a squared x squared plus b squared. Add this with a squared divided by b, and then arctan of a times capital N, and then divided by b, then subtract b multiplied by the natural log of a subtract b. Okay, and then so now we just take the limit to this entire thing. Now this one over here, of course, you can probably tell that we're gonna actually get into the form of an indeterminate form, but again, this is another one I'll just leave as an exercise for you guys to follow, since it's more, work that can be easily done. So if you actually apply all that stuff, L'Hopital's rule, we're gonna get that this is b times the natural log of b divided by a. So I'll write this per L'Hopital's rule. So now we have that in mind, so that means we still have to take the limit as n approaches infinity for over here as well. So then continuing, so I have 1 divided by a to the power 4 plus b to the power 4, then b multiplied by ln of b divided by a per L'Hopital's rule from this evaluation over here. Then over here, this term, this is going to be pi times a squared, then divided by 2b, and then still left with b, then natural log of b divided by a, then minus b times the natural log of a divided by b. Okay, so now we have that, and then still we can simplify even further if we want to, so let's do that. So then we have equals 1 divided by a to the power 4 plus b to the power 4, because they're both natural log functions over here. Then we're going to have that this is going to be 2 times the 2 times b. Since it's because it's a minus, then I can actually just flip the terms around so that becomes a positive from using the natural log term, so that's how we get a double instead. 2 times b times the natural log of b divided by a, and then add this with pi times a squared divided by 2b. Okay, so that is actually our closed form for u of ab, but we're actually not done because, of course, the question being asked, or what we're being told, is we need to calculate the limit, L. So that's where our next step is going to be. So then we're actually going to call L, AB a function. So let's see, L comma a or L of a comma b, we're going to let this be equal to our u. So if we input the function, so u, so we're going to let this be b minus a or b comma a, and then on the bottom we'll let a comma b. Then we're going to take that as 1 divided by a subtract b. Okay, so then that means we have to plug in everything from this generalized term that we put in right here. So I'll underline this, to underline that, to actually confirm that that is the generalized form that we found. So in doing so, that means we're going to have the following. So this is going to be a long one, not really long, I'm just over exaggerating. So we're going to have 2a multiplied by ln of a divided by b plus pi b squared, and then divided by 2a, then divided by 2b ln of b divided by a. Add this with pi times a squared divided by 2b, close that off, and then 1 divided by a subtract b. And so then what we can do here is let's actually take the natural log of both sides. So then we have the natural log of capital L A B over here. So of course that just means I could just move the exponent 1 divided by a minus b to the front. So 1 divided by a minus b, then times the natural log of the same thing over here, 2a ln of a divided by b plus pi b squared divided by 2a, all this being divided by 2b ln of b divided by a, at this with pi times a squared divided by 2b. Okay, so there's that. And then with that being the case, let's actually now take that limit as we're actually going to let b approach a in this case. I know it's kind of weird to say this since we have that, if we just go back to ja and ka, we have that in terms of b is like 1, but that's just going to lead us back to the beginning and that's not going to get us anywhere. So we're actually going to let this conceptually, we'll let b approach a, so that way as you take that limit, the b will be isolated on its own, such that we're just going to have a as the variable on its own, and then that'll make things easier to actually calculate the limit that we're supposed to calculate. So that means if I take the limit, so the limit as b approaches a of the natural log of a comma L of a comma b, then you're going to note that this is actually going to be a 0 over 0 indeterminate form. And I'm going to leave this as an exercise for you guys because this one is a pretty long one to show as well. So L'Hopital's rule over here, we'll write that a little better. So we're going to leave that as, I'm going to leave that as an exercise for you guys. But once you actually do that, so I'm going to use this last line on the top over here. So that means if I take that limit, so the limit as b approaches a, so I'm going to just rewrite that again one more time, then we're going to get that this is actually going to equal to 8 divided by pi minus 3, and then all this being divided by a. And so therefore, if you actually just take take the e base of both sides, so that means I have that L is equal to, now we can actually take this as the limit approaches a in this case. So the limit as a approaches a of e to the power 8 divided by pi minus 3 divided by a, which therefore if you just let that approach, then that means it's simply just going to be e to the power 8 divided by pi minus 3, which therefore that is the final answer to our limit that we're being asked to calculate over here. I know it's like, again, as I mentioned, there's a lot of like, I think there was like 3 of those steps I mentioned that I'll leave you guys as an exercise, because a lot of that stuff is like, it's basic knowledge, but it's like a lot of long-term work behind it that there's really no need to, you know, go too beyond that. But I just wanted to generalize and pose the idea on how we actually approach such problem over here to get, just so you guys have an understanding on how to like take a look at things from like another way of another perspective. So basically we just call our integral over here. Just notice that this is just similarity as we just plug in the values in. We break this down by partial fraction decomposition. So let me actually write that down over here. Partial fraction decomposition, just to abbreviate. Then take its limit / calculate the definite integrals that leads to over here. That was a long line of work. Call function. Then we actually just, you know, take the natural logs and then try to approach this by using L'Hopital's limit to get that indeterminate form to approach this step. Then it's pretty much smooth sailing from over here to actually figure out the rest from there. So yeah, that's pretty cool if you ask me.